announcements before we start class. Just keep in mind the new due dates. Group data, it's a fairly small homework. There's only 6 questions on it. So that's going to be due Wednesday. And there's also a quiz for central tendency, dispersion, and grouped data. So it's got a lot of material involved with it. That homework, or that quiz rather, is due, it's going to be due Friday. 1 second. Got to change that. Okay. So that's going to be due Friday. So just keep that in mind. Does anyone have any questions for me before we get started? If not, today's going to be a fairly laid back lecture, because really we need to establish a bit of terminology before we look at what we're going to be talking about on Wednesday. We'll see that in the next section. Also, this section, though, we'll look at really something that does come up that should definitely be considered, which is, so we've been talking about the mean and the standard deviation mainly, as well, the mean being a form of a measure of central tendency that we use a lot, and standard deviation, a measure of dispersion. The question is, though, if you are presented material in a frequency distribution, you can sort of foreshadow this in example 1. Notice that they do not give you any raw data. They tell you how many observations occur in a group, not just a category, a group. So so for this example, in example 1, a baby that weighed 800 pounds is treated the same as a baby that weighed 500 pounds, or not pounds, grams. And so with that comes the issue of how would you be able to find the mean and the standard deviation of these quantities? Because these quantities are represented by a range of values. So really, I suppose when you first look at this, there's no way to really determine the mean or standard deviation of this, because these frequencies can refer to any one of these values. This is known as grouped data, data that is categorized by groups rather than just a singular category. And we've done this before. This is, we generally do this with continuous values or discrete values when there's a lot of them. But the way we can approximate a mean, not figure out the actual mean, without actually having the raw data to add together and then divide by the number of values, the way we actually do this, or one way we do this, is called using a class midpoint. And so the class midpoint is a way to take subsequent rows, or rather a class, and average it. So that way you're sort of calling the group of that row, you're referring to that group as the midpoint between consecutive lower class limits. So it's a way to really take a group and average it out, so that way that average or that class midpoint can be used to help you approximate a mean and a standard deviation. And this mean will, well, this average will be the best form of computation for us. And we'll see how also to do this in the calculator as well. So, so for example 1, let's go ahead and look at exactly this. So as I was mentioning before, this table of values, they give us grouped data. So that means where the classes are intervals. And this is a frequency distribution. They're just telling us they took a whole collection of data. and they counted how many occurrences in each interval. So pretty straightforward stuff. The first question they want us to determine for this collection of information is find the class midpoints for each class. So this is where we're going to introduce new material here. So the class midpoints, it's a way to take the group here and sort of average it out. And this average that you're finding, so remember, it said the consecutive it's the average between consecutive lower class limits. So to figure out that class midpoint, consecutive lower class limits would be 0 and 1,000. Those are the lower limits for their respective classes. So you need to find the average between those two, which by identifying that, you'll see very quickly, this is 500. And then the next one, it's the average between consecutive class limits. That's between 1,000 and 2,000. Those are the consecutive class limits. And you keep going down in that order to get each subsequent value. So this would be 1,000 plus 2,000 divided by 2. And that would be 1,500. And you might already see the pattern here. I'll write out one or two more just in case. And then 2,000, the average between 2,000 and 3,000 would be the next class midpoint. So that will be 250. And then the next two should be obvious because it follows the same exact process. And the final one, you might see a pattern here and might see what the final one is. But I want to make sure you see why it is the value that I'm going to write down. So when we're trying to figure out the class midpoint for this final row, your question is, all right, it's the average between that lower limit and the next lower limit. But there's not a following lower limit. So instead, you have to sort of guesstimate what it would be in this case. So if this value ends at 59.99, next one, it's safe to assume it would be 6,000. And then that's why 5,000 plus 6,000 divided by 2, that's where you would get your 5,500. So it's a way of finding the average between the groups, and then that average will help us approximate a mean and standard deviation. Is that pretty straightforward so far? And like I said, today is going to be just pretty laid back day, I think. So part B is approximate the mean and the standard deviation. So now we're going to use these class midpoints to approximate the mean and standard deviation, not determine it, but approximate it, because the class midpoint is just used as an approximation metric. And so there is a process fairly similar to what we did in the calculator before, but we're going to modify it slightly. So if you scroll down a little bit, or if you have your notes printed out or whatever the case is, yeah, so go ahead and get your calculators out if you haven't already. We're going to go ahead and figure out how to find finding the mean and the standard deviation of group data. So that's ultimately what we're doing here. I'll pull out the virtual calculator as well. Depending on which calculator you have, this might be slightly different, and I try to write both situations down. If you have the 83 plus, then you can follow along directly. If not, I try to add another picture in here. So if anything, we're going to start off stat and enter to go straight to your where you input data for your lists. In L1, that's going to be, in the first list, that's going to be where all the class midpoint values go. So all these class midpoint values that we found, the 500, 1500, all of those, all the class midpoints go in the first list. So let's just go ahead and type those in right fast. So it's 6 values, pretty quick. So that's the first one. The second column are the frequencies. The second column is going to be the frequencies that were given in the beginning of the problem. That's going to go in the second list. So again, pretty simple stuff. So move your cursor over to the second list. That's 27,000, and we just keep going. And as you would imagine, you want these lists to be the same size. The class midpoints are basically averaging the groups. And with that, they're going to have corresponding frequency measures or values. So far you should have list 1 and list 2 filled out by now. So once you have those filled out, you're going to quit out the screen. So second in mode, so second and quit. And you're going to go back to stat and go over to one variable stat. So we've done this part before, but do not press enter here. And depending on what calculator you have, this might be a different, so I guess for the people in class, how many of you see exactly what's on the prompt here? And if not, do you see, does it say list and FREQ list? That's what you're, okay, so I'm gonna accommodate both of you. I'll start off with people who see this. So if you see this, and I wrote this down on here, I think it's TI-83 or 84 pluses. There's some that are silver edition and some 89s or whatnot. Point is, if you see this, you're going to press the following. Second, and then just 1. And then this L1 is going to pop up. So just second and 1 for that L1 to pop up. And then you're going to press comma. There is a comma button over here as well. And then second and the number 2. If you did all that correctly, you should have exactly what's on my virtual calculator here. Is there anyone who is not able to figure that out? So if you figured that out, go ahead and press enter, and you should get these values. So make sure you get those values. If you did, you typed in everything right. If not, make sure you go back and check what you have. So if you have the other situation instead, so if you have something that looks more like this picture down here that looks different than the other pictures. So I'm not going to be able to resemble that on this computer, but under list, it should say L1 already. Under frequency list, when you put your cursor there, you need to press second and the number 2. And it needs to look just like this. So if you have a calculator that displays something like this, it should say L1 for list already. But under frequency list, you need to press second and just the number 2. And then you press enter until this stuff comes up. Is there anyone who cannot figure this process out? I'm going to assume everyone can figure this process out. Whatever the case is, whatever calculator you have, you should get the following numbers on the screen. And these are the approximated mean and standard deviation using class midpoints. Or in other words, this is the approximated mean and standard deviation of grouped data. And this is the exact process for doing so. In particular, what we care about, so what are we looking for again? It's the approximated mean and standard deviation. Caitlin, I'm going to go ahead and mute you. I think your mic turned on. Okay. Cool. So from here, the mean and standard deviation, the mean is just x bar. That's the sample mean notation. This is 3, 2, 8, 1. We'll call it about 0.5. Just round in 1 decimal place. And we'll go ahead and use the sample standard deviation. So sample standard deviation is denoted with an S, but in the calculator they call it SX. So I have both notations here. I mean, the numbers are virtually the same. 648.18. So if you have those values on your calculator, then that means you did everything right. Does anyone have any questions about this before we look at another example of this? If not, let's look at a situation where the groups are not uniform, as in some of the groups are larger or smaller than others. So there were US citizens 50 and over that were surveyed about when they expect to retire. And then here were the anticipated ages that they provided. And so sometimes they have irregular group sizes whenever, so 65, that's normally a pretty common retirement age for Social Security. So it's expected that 65 on its own will have a lot of retirees. So for part A, we're going to determine the class midpoints of all of these, because this is group data again, as in the classes or intervals. And if we want to approximate the mean and standard deviation, we need to take the intervals and just get one concrete number out of them. So the class midpoint, it's the average between consecutive lower limits. So the first one, the consecutive lower limits are 56 and 60. Guessing this is 58. (56 plus 60 divided by 2 is 58. So 58, and we keep going. So the next class midpoint is the difference, or the average rather, between 60 and 63. That should be 61 and a half, I believe. 60 plus 63, 61 and a half. And then what about the next one? So the next row would be the average between the lower class limits, but there's just a 65 by itself. Well, that just means it's the lower class limit and the higher class limit. So we can use 65. We're going to treat it as if it were the lower class limit. So that would be 63 plus 65 divided by 2. That's 64. And then, of course, the next one is going to be 65 plus 66. And we can just go from there. I don't think I have to write out anymore. 65 and a half. And then the next one should be 67. And the next one should be 70. And then the final one that we obtain would be the difference between the midpoint or the lower class limits of 72 and whatever number would naturally come next if this list were to continue. So it goes from 72 to 75, so naturally 76. I believe that's 74. So again, pretty straightforward stuff, regardless of if the class sizes are uniform or not. We apply it the same exact way. It's still just the average of the lower consecutive limits. And from there, it's the same idea. I think I hear some of you typing already, so that's perfectly fine. We'll go right into putting this into the calculator and determining the sample mean and sample standard deviation. So remember, you can clear a list by moving your cursor up to the name. Oops. Pressing clear, enter. Do the same thing for this one. Remember, the first list are the class midpoints. And the second list are the frequencies. So let's do that. Second list are the frequencies, 31, 67, and we keep going. Again, you want to make sure that your list sizes are the same, or you might have typed in an extra value or missed a value. It should definitely be the same. Quit out of that. Go back to one variable statistics. You have this screen, second 1, comma, second 2. Is anyone having trouble obtaining these numbers? I'm going to assume that the silence is in favor of everyone understands this process. If not, it's okay to ask. Don't mind helping out. Okay, well, given all of that, and again, if you forget the process, I have it pretty explicitly up here. So from here, all we need are the sample mean and the sample standard deviation. So again, we just read what the calculator tells us. Sample mean, call it 65.8, just around the 1 decimal place, doesn't really matter. And the sample standard deviation, we get 3.4. Again, the sample one is what they explicitly ask for. The population one is pretty much the same, but they want the sample standard deviation. And in general, that's what we use the majority of the time for standard deviation, is the sample one, unless they specify population one. Does anyone have any questions up to here? If not, that's already a third of the homework right there. So let's move on to example 3 then. So example 3 talks about how professors actually, or even my math lab, calculate grades. So when grades are computed, so you might remember for this class, if you go look at the syllabus, there are grade distributions. So I believe it's 20% homework, 20% quizzes, 20% first test, 20% second test, and 20% final. It's something like that. What are those percentages? And that's true for any class. Those percentages are weights. Those are known as weights. What weights are, it gives certain quantities more contribution to the final grade than other ones. So if a grade is worth, if you took 105 last semester, you might remember that the midterm was worth 30%. It was 30% of your grade. So was the final. That meant that this weighed a lot more than a workbook grade, which was only 6% of your grade. Those weights are considered when professors find a final grade over the course of a semester by the process we're going to be talking about here momentarily. So what a professor does is figures out the grade in each category, figures out your homework grade, your quiz grade, your exam grades, and so on and so forth. These grades are then weighted, which we'll talk about here in a second, and then dividing by the sum of the weights. This is, in essence, this is kind of this idea of grouping data together. Weights are some application of this. And we'll see how professors do this. We'll see how MyMathLab is programmed to do this and how it computes this so quickly. So let's say there's a random course on Southeastern's campus where the homework is 15% of your grade, quizzes are 10%, exams are 60%, and the final exam is 15%. In fact, if you took Math 105 last semester, you might remember a question very similar to this. If a student has 100% for homeworks, 87 for quizzes, 79 for exams, and 80 for final, what is the course average? So what the professor does, so for example, the homework grade was 100%. So the grade, so it was 100% for homework, but then when this is weighted, it's multiplied simply by its weight, which was 15% for homework. And since all the quantities in this problem are percentages, we don't have to convert to decimals. We're dealing with nothing but percentages, and our final answer is going to be a percentage, so we don't have to convert to decimals. If you did, you'd have to just convert right back. So that takes care of homework, and so this is a weighted mean situation, so that means we're adding. So the next situation, quizzes are 10%, and this person got an 87% for quizzes. So that student got an 87% for quizzes, but this needs to be weighted. And then the next one, exams are 60%, and the student got 79% for exams. So they got a 79 for their exams, and that's weighted by 60. Finally, final exam is 15%, and they got an 80% on the final. So they got an 80 on the final, and that's weighted by the 15. So it's these weights that really change. So the percentages that the student gets in each category, not all of those values are the same. They're not weighted the same. So that's why you have to throw in these weights to translate them to what they really represent. So then you have to divide by the sum of the weights. So the sum of the weights, that would be the 15% for the homework, the 10% for the quiz, the 60 for the exam, and the 15 for the final. So in the numerator, it's the sum of the weighted means. In the denominator, it's the sum of the weights. So let's go ahead and figure out what this number comes out to be. $8,310 divided by 100, which comes out to be 83.1%. So that's how grades are computed. This is the exact algorithm that MyMathLab is given, provided it is told the weights of each category, and that's how MyMathLab computes this, or any professor. They normally use Excel or something to compute it generally, or Moodle sometimes do it for you. Does anyone have any questions here? Okay, we have a little bit of time. My Robinhood guys, what's hot on the market right now? Where's it at right now? Go ahead and look it up. We have a little bit of time to kill. Because I'm in Dogecoin right now, so tell me what tell me where I'm at right now. Let's see.
It's 7.9. It's almost 8.
Now this would be the best time to sell. I was thinking about selling at 8. So hoping it wouldn't bump up to 9 behind my back. Oh well. All right, that's good to know. Well, also Bitcoin went up a lot. Tesla said they're going to be pumping $1.5 billion into the infrastructure of Bitcoin. So that went up predominantly much. Okay. Well, I guess let's get back on track here. We'll move on. So this section we just finished is, like I said, the homework is due Wednesday. There's only 6 questions, and I just talked about 3 of them here. The other 3 should be fairly similar. So that, again, that homework's due Wednesday, so don't forget that due date. We're going to move on to the next section, which is on position and the 5-number summary. And so this section, we're not going to finish it today, but we're going to talk about, there's a lot of terminology that we need to introduce here. And that will help us with the next class period. And so we'll start off with position. And position is very much correlated with the standard deviation that we talked about previously. The standard deviation gives us an idea of the dispersion from the mean. And what position represents in this case, a measure of position. So each data value has its own specific distance from the mean or standard deviation from the mean. And there's actually a way we can determine this position. So sometimes you don't care about a value qualitatively, but instead you care about the value relative to its displacement from the mean. It tends to be used a lot in curving grades. There are many other categories in which this is used. Ultimately, any normal distribution where there's no skewed data whatsoever, you are able to determine anomalies based off of distance from the mean. And so you don't care about the number, but how the numbers compare to the average. And this value, this measure of position, is called a z-score. It's called a z-score. It's a very important idea. We're going to be using it for the remainder of the semester here. The z-score, it's a very important idea. You might remember it from Math 105. It simply represents the number of standard deviations an observation is from the mean. So if a number is told to be, if a value is said to have a z-score of 2. It means it's 2 standard deviations from the mean. There's 2 types of z-scores, a population and a sample one, but the formula is exactly the same. The formula is exactly the same. You take the value, you subtract the mean, and then you divide that difference by the standard deviation. The only difference between the 2 formulas is, do you use the population mean or the sample mean? Do you use the population standard deviation or the sample standard deviation? It just depends on the circumstance. A lot of the introductory problems will just tell you what the standard deviation is, and you don't have to worry about that. So let's look at example 1 and determine what this represents. So example 1 says the average 20 to 29-year-old man is 69.6 inches tall with a standard deviation of 3 inches. So they just gave us the mean and they gave us the measure of dispersion. They gave us the standard deviation, which means that approximately 68% of men from 20 to 29 will fall between the heights of 66.6 inches and 72.6 inches. That would be 1 standard deviation below and 1 standard deviation above. Additionally, the average 20 to 29-year-old woman is 64.1 inches tall with a standard deviation of 3.8 inches. So there's a little bit more spread here. It's a little bit more diversity of heights in that situation. So it's clear here that the average man is taller than the average woman, but the question is, if you take a man and a woman with some heights, which one is relatively taller? Which one is taller compared to their particular group? Would a 75-inch man be relatively taller in his category of other men compared to a 70-inch woman in that comparison? And that's what standard deviations allow us to see. The book explains it as it allows you to compare apples to oranges. I think that's a good way of summarizing it. You can sort of quantify a spread of data by using z-scores. So to figure out the z-score, so normally the notation, so this is for, we'll start off with men. The z-score, the way it's normally notated is z with a subscript of 75, because we have a 75-inch man. So it's the z-score of a value that measures 75. And so the formula we use, 75, again, just the value you observed, minus the mean. They said the mean for men was 3.0 inches. And then all of that is divided by the standard deviation. Oh, I'm sorry. I got that switched. The mean was 69.6 inches, sorry. And the standard deviation is 3 inches. This quotient will give us the z-score. It's a very simple computation. If you put this all in your calculator at once, make sure you use parentheses. Because what you should get from this is 1.7. So make sure you type it in your calculator correctly. Remember, calculators don't understand a numerator and denominator unless you tell it explicitly. But you should get 1.7. So standard deviation is not it doesn't have a unit of measurement. You don't say that's 1.7 inches. The standard deviation is just a number. And what this says is that a 75-inch man has a z-score of 1.7, which means that height is 1.7 standard deviations above the mean. Now let's look at the woman. So here's Z-score. I'm going to do Z with a little 70 next to it because we're observing a 70-inch woman. This is 70 minus the mean for women, which is 64.1 inches tall, divided by the standard deviation for women, which was 3.8 inches. And this gives us a new computation to consider. And we can round that to 1.6. Now, the question was, who is relatively taller? It's going to be the observation that has a larger Z-score. So it's going to be the man in this case. So the man is relatively taller. So again, this is allowing us to compare apples to oranges. This is a way of comparing men, or a man to fellow men's heights, and then a woman to fellow woman's heights. And then that Z-score gives us some metric, some shared metric that we can share among different values. It tells us I suppose the orthodoxy or, well, unorthodoxy of any particular value relative to a mean. Does anyone have any questions about the Z-score? If not, let's recall the median. Let's bring the median back up. So the median is a measure that we didn't talk about this too much before. It did come up, but we're going to emphasize this fact about the median. The median is a measure that divides the lower 50% of the data from the upper 50%. The median is a type of percentile, which we're going to define here, as you can see momentarily. So the median, remember the median determines or is a resistant measure. The median only cares about the number of data points instead of the quality of the data points. But what the median also consequently does is it is a divider between the lower 50% of data and the upper 50% of data. So by providing me the median, you're telling me a boundary that separates the top 50% from the lower 50%. And this idea is known as a percentile. The kth percentile is a value stated such that k% of the values are less than or equal to that particular value. You explain what that means because that just sounds very technical at first. So I'm guessing everyone in here took either the ACT or the SAT. Whenever you took the ACT, they gave you not only a score, I believe there's a quantitative, I'm getting that mixed up with the GRE. There's a math and a reading score and a writing score. I can't remember anymore. I took it way too long ago. But they give you a percentile score for each category. So for math, they give you a percentile score. Composite, I remember the composite one mainly. So your overall cumulative performance on the ACT, they gave you a percentile for that. And it may have been the 85th percentile. Now, what does that mean? So I checked recently an ACT score, a composite ACT score of 27 is in the 85th percentile. And then the question we consider is, what does that mean? Simply, what that means is 85% of ACT participants scored, oops, not scores, scored less than or equal to, scored less than or equal to the provided observation. Or I guess, since they do state the provided observation, we're equal to an ACT score of 27. That'd be more appropriate. So if you score in the 85th percentile, you're better than 85% of people's scores. That's pretty much it. If it's 25th percentile, you're better than 25% of participants. That's all it means. It just tells you what percent you're higher than in some category. So we did say that the median is a percentile. What type of percentile would the median be? So that's a question I ask you all. What type of percentile is the median? It's the 50th percentile. Median is the 50th percentile. It's the 50th percentile because it separates the lower 50% from the upper 50%. But also, if you score the median value, that means you scored higher than 50% of data, whatever the data may represent. So the median is the 50th percentile. Okay. Again, like I said, today is just a lot of terminology, and it's all going to apply to next class period. We're going to move on to quartiles. Again, if you took 105 last semester, all of this should look very familiar. Quartiles are specific types of percentiles. As the prefix QUAR indicates, it's going to be something with fours. And in particular, quartiles are percentiles that divide data sets into fourths. Quartiles divide data sets into fourths. There are 3 quartiles. And the quartiles, as you would imagine, these quartiles are boundaries that separate the data into fourths. There's the first quartile, which divides the bottom 25% from the top 75%. Naturally, the first quartile would be considered 25th percentile. The second quartile divides the bottom 50% of data from the top 50%. That may sound familiar. In fact, it is. The second quartile is just the median. So the median is a quartile because by definition, it helps split the data into fourths. And there's a third quartile, which separates the bottom 75% from the top 25%. Those are the 3 quartiles. Those three data values help divide the data into 4 sections. And this helps build up to something we'll talk about here momentarily called the 5-number summary. But in the meantime, here's a question. Are quartiles resistant? So think about it. Are quartiles resistant? What does it mean to be resistant?
No, I don't think so.
You don't think quartiles are resistant? So what are you claiming here? What does that mean to not be resistant?
Because if there's a number at the bottom of the set, it may screw up, or like an outlier may screw up the quartile.
So you're saying not resistant. So your definition of resistant is correct. If you're not resistant, then an extreme value will really screw up your data. If you are resistant, then an extreme data value will not mess up your data. So it turns out, so remember, one of the quartiles is the median. Does anyone remember if the median is resistant or not resistant?
Median's resistant.
The median's resistant. So guess what the other quartiles are going to be? Resistant. The reason why the quartiles only care about the number of values and not the size of the values, just like the median does. So if we're able to chop up some value into fourths, so if we're able to chop up a value into fourths and you add some extreme value at the end and take away another value, those boundaries are not going to be prone to change very much, just like the median. The median's a quartile, and as such, the quartiles are derived from that premise. So the quartiles, they are resistant, i.e., they do not change much. They could change, but it would be very minuscule when extreme values are introduced. And the best way to remind yourself of this, because I might ask a question on the first test and it'll just be a random measure or maybe two random measures. And I'll ask, is this one resistant? Why or why not? Is this one resistant? Why or why not? And for the quartiles, well, ultimately, they just care about the number of values and not they care about the number of values and not the quality or the magnitude of the values. Again, another way to help you remember this, median is a quartile and median is resistant. The quartiles, the other quartiles work in the same exact way the median does. Does anyone have any questions up to this point? If not, there is a measure of dispersion. So another measure of dispersion, we had the range, the standard deviation, and the variance. There's technically another one called the interquartile range. So the interquartile range is technically, well, maybe not technically, it is another measure of dispersion. And what it does is it measures the range of the middle 50% of the observations. So it's denoted IQR. It's the range of the middle 50%. So in other words, the middle 50% of the data is measured. Well, 50% of the data right in the middle is in between the first quartile and the third quartile. So it's between the first quartile and the third quartile. And the difference between those two is the interquartile range. Inter meaning between, quartile meaning, hey, it's quartiles. Range meaning difference of. So it works out really nicely, like how medical terminology does. So as it says below, the interquartile range is a measure of dispersion, as I mentioned. So this measure, though, the reason why this number that you would get is so helpful is because it helps us determine outliers. So I've heard a few of you mention the word outliers before. If you don't know what outliers are, it's just extreme values. So it does have a brief definition here for outliers, extreme values in a data set. But that sounds like a fairly relative thing to say. How do you know for certain if a value is extreme? Now we can use intuition. How would a computer know? How do we give a computer some sort of way to understand what outliers are? Us as humans could say, wow, 1 million is a lot more than this value of 27 through 35. But the way that this is done in a more concrete manner is this IQR contributes towards how to find fences. Fences are exactly the boundaries for which the expected or typical values, or in other words, non-outliers, fall in between. If values fall outside of the fences, they are considered outliers. And there's other methods in practice used to find outliers. This isn't the only one, fences, but this is going to be the predominant one we look at in this class. So fences are boundaries that help identify ordinary data that should belong in that set. And there's two types of fences. Of course, there's a lower fence. And notice how these are computed. The lower fence, notice it requires you to know the quartiles and the interquartile range. There's also the upper fence, which also is very similar. One's a subtraction and one's an addition. But those two values, the lower fence will be a number, the upper fence will be a number. And together, those two numbers will provide the boundaries for which the ordinary data falls into. If a value does not fall in between those two numbers, it is considered an outlier by this definition. And all of this comes full circle to the 5-number summary, which we will talk about in greater detail next time in class. But here, the 5-number summary, it's, well, as you would imagine, 5 numbers. These 5 numbers are boundaries that separate any data set into 4 equivalent regions, or in other words, each region contains 25% of the data. So if I were to ask you, what percentage of data falls in between the smallest data value and the first quartile? It's 25. Or if I asked you what percentage of data fell between the first quartile and the third quartile, there's a 25, there's another 25. 25 plus 25, 50. Or what percentage of data falls in between the first quartile and the largest data value? It's 25%, 50%, 75%. It's a pretty simple thing. Again, you might remember that from 105. But we're not really going to focus on the computation today. Today was really a terminology day, and the next class period is going to be a more computational heavy day. So now that puts us in an interesting position because I'm out of notes. Don't pack up yet. I'm out of notes. We can go about this in one of two ways. I can open up group data. You can look at the remaining homework, get a good idea about how that goes, or we can get out early.
Yeah, I'll leave it early.
Well, I know you're down for leaving early. If you want to leave early, you can leave early. If you want to stick around for a little bit of a review session, then you can go ahead and do so. But I'll give you a few minutes to decide that. I'm not recording this part though, so consider that one.